In the next few minutes, I will be talking about a new method that I have devised for solving optimal control problems involving different types of constraints. In this presentation, I will be focusing on atmospheric flight mechanics domain, but in case you have an optimal control problem from any other domain, you can still solve them using this unified trigonometrization method. First, I would be setting up the motivation for this study. There are different methods to solve trajectory optimization problems, but in this presentation, I will be focusing on a particular set of methods known as indirect methods of optimization. These methods have certain issues because of which the research community have not used them a lot. But recently, there have been certain advancements that have resolved these issues. So using these advanced indirect methods, I have developed the unified trigonometrization method, or the UTM, which involves 6 steps. Using these 6 steps, we can solve optimal control problems pertaining 3 different classes. In the first class of these problems, the controls appear in a bang-bang and or singular form. In the second class of problems, the constraints are upon the controls and the controls appear in a nonlinear form. In the third class of problems, which are actually the most complicated from among these 3 classes, the constraints are upon the states of the problem. For each of these 3 classes, I will be showcasing an example of how to implement the UTM. The results obtained for these example problems using the UTM are verified and validated using a pseudospectral method based direct solver called GPOPS2. So in the end, I will be laying down the future work for this study and summarizing this presentation. While solving trajectory optimization problems, the research community resorts to 2 different methods. One are the direct methods and second are the indirect methods. Now, direct methods are more popular because they are intuitive and easy to use. In these, basically, we transcribe the original problem into a nonlinear programming problem and we solve for the states and the controls directly. While the problems have constraints of different kinds, these are much more efficient to handle such kinds of constraints, but all these ease of implementation comes at a cost. These direct methods do not employ the first order necessary conditions of optimality. Therefore, they do not guarantee that the solutions obtained would be optimal. They will give you a solution, but there is no guarantee that it would be optimal. This is where the indirect methods come into picture. These methods are way much more complicated and difficult to use because they employ the first order necessary conditions of optimality, which require certain more equations. But all this hard work and these extra equations lead to high resolution solutions, and the control law that we obtain is of a closed form, which provides much more insight into the solution. So therefore, these indirect methods are attractive because of their advantages. Now, when you are trying to solve your optimal control problem using indirect methods of optimization, you have to start with minimizing an functional, which is written as J here, and it includes a summation of the terminal cost or the initial cost along with the path cost, or a Lagrange. That's why its name is L. And these are subjected to certain equations of motion for these states or the dynamic constraints, and there are certain initial and final conditions upon these states and times. Now, using all this information, we evaluate something called the Hamiltonian. This is a mathematical quantity which involves the path cost as well as something called the co-states multiplied with the equations of motion. Using all that information, we evaluate this set of equations known as Euler-Lagrange equations. The first equation is actually pertaining the control law, and the second equation pertains to the dynamics for the co-states. So these methods are called indirect methods because the co-states determines the controls and the controls determine the states. So indirectly, we are able to get the states from the co-states. Now, when we have more than one control option available, the traditional method suggests that we use Pontryagin's minimum principle, which states that we choose that control which minimizes the Hamiltonian. So the best control is the one that minimizes the Hamiltonian from among all the options. Now, when we are trying to solve optimal control problems involving constraints, where the constraints are of this form, then there are two subclasses of problems. The first one where the controls appear in a linear form. And then there is something called the switching function, which is h1 here. So it's popularly known in literature as switching function. So when we take the derivative of the Hamiltonian with respect to the control, we obtain this switching function and the control disappears. So we cannot get a closed form solution for the control law from here. So what we do is we use Pontryagin's minimum principle, and then we obtain the optimal control law based on the sign of the switching function. The problem appears when the switching function becomes 0, and anything multiplied with 0 will actually satisfy this condition, which will minimize the Hamiltonian. So the control could gain any value, and then the problems become singular in nature, and that's why it's called a singular control problem. So there is a non-uniqueness issue here, which I will be discussing in a future slide. There are other class of problems or other subclass of problems where the control appears in a nonlinear form in the system of equations, and there are constraints upon this control. So what we need to do is we need to augment the Hamiltonian with these extra constraints, and then you see the extra multipliers emerge in these, and then we need to solve for this more complicated version of the Hamiltonian and get these new dynamics for the co-states and solve for a multi-point boundary value problem, which is very tough to formulate. Now an even more difficult version of the problem is where the constraints are upon the states and they appear in this form. So traditionally what we need to do is we need to take the time derivatives of this expression until the control appears explicitly in this equation. So in this picture, if you see, the control or the solution is unconstrained at first, and then the state constraint is active, and then it is again an unconstrained solution. So we need to modify this Hamiltonian and augment it with this extra multiplier multiplied with this qth derivative of s, which will give an explicit function of control, and thereby we need to calculate these Euler-Lagrange equations for the modified Hamiltonian. So these are the new optimality conditions, but along with that, the complexity is at these junction points, at the start of the constraint and at the end of the constraint. We need to have the continuity in the states. At the exit, we need to have continuity in the co-states and the Hamiltonian. And then at the entry of the constraint, we need to have these extra conditions where there can be jump in these co-states and the Hamiltonian. And these are additional tangency constraint conditions upon this problem. So overall, the gist of this slide is that these set of problems or this class of problems are very complicated to solve. And then the literature also suggests that we need to use these additional necessary conditions of optimality, which have or showcases a relationship between the jump multipliers along with the multipliers corresponding to these tangency conditions. So we solve for a multi-point boundary value problem again, which is very tough to formulate. So the literature suggests or cites three major reasons or three major issues why indirect methods have not been used by the research community. The very first reason is that you need to know the optimal control theory, which is very complicated. And in the last 3 slides, I have shown you how much complications are involved. Second thing is that when we are solving a problem involving constraints, we need to have an idea about the structure of the solution even before finding out the actual solution. So in order to give a good guess, you need to know that the constraint is initially inactive and then active, then inactive, and so on, which is a complicated process, and we don't have prior knowledge about these things. Also, when we are trying to give a guess to this problem, we know that indirect methods have a lower convergence zone. So that means we have to give a very good initial guess. Now, when we are giving initial guess for real world things such as altitude, velocity, we can actually think of something because these have real world meanings. But when we are trying to give a guess for co-state of altitude or co-state of velocity, these don't have any physical meaning. They are just mathematical quantities. So then it's very hard to guess such things, such as the co-states. So therefore, there are these difficulties with the indirect methods. But there have been certain recent advancements which have been employed in the proposed method called the unified trigonometrization method, which I will be talking about in next slides. And what are these advancements? The very first advancement is that we can actually automate the process of obtaining these extra equations by using symbolic computation toolboxes, such as those available in Mathematica and MATLAB. So you don't really need to know the optimal control theory and its complications. Second thing is, while dealing with the problems involving constraints, what you can do is actually, instead of solving for a multi-point boundary value problem, you can just solve for a 2-point boundary value problem and impose the constraint using the implicit bounding properties of certain functions, such as trigonometric functions. And regarding the third issue, instead of giving an initial guess for the entire problem, what we can do smartly is we can just solve a simpler version of the problem, where even if we give a bad initial guess, we would obtain a convergence, and we can then use the solution of this simple problem as an initial guess for the next complicated version of the problem, and then we march this complexity until we solve the most complicated form of this problem or the original problem itself. So this is called the numerical continuation technique. So now we can get around these three issues which have been cited by the literature. And that brings us to this unique new method called the unified trigonometrization method. As the name suggests, it uses trigonometric functions to place implicit bounds in one way or the other, or act as penalty functions. But before I go ahead, I would like to say that we don't claim that we can solve all types of optimal control problems involving all types of constraints. Moreover, we have not employed all types of trigonometric functions, so there might be some more which are existing out there, but we have not found so far any other trigonometric way of solving these kind of problems. And the third thing is, this is not to downplay the direct methods, because indirect methods and direct methods have their own advantages and disadvantages. This is just to have a look into indirect methods of optimization and have a much more focused approach to develop these methods more. So when we are using this UTM, or unified trigonometrization method, and while you are trying to solve your optimal control problem, in such a problem, most likely you will have a constraint upon the control, because you are trying to solve a real world problem, and there will be constraints upon the control. So then all you need to do is you need to change your control from its original form and map it to a trigonometric form. So all you need to do is change U to a U trig, and this U trig has a sign wrapper around it. So that ensures that whatever value U trig takes, sin U trig will ensure that it is between -1 and 1. So that is using the implicit bounding property of sine function. So all you do is you start with U, but then you just map it to U trig. In the second step, you modify the path cost of the Lagrangian using trigonometric terms. So when you are dealing with problems involving bang-bang and singular controls, you need to obtain a smooth structure for your control. So then you need to introduce a small amount of error. And if you see, there is an error parameter and an error term, and the error term is also of a trigonometric form. So this error control is also of a trigonometric form. Also, this second term here, this is used for placing bounds on the constraints that are on the states. So in order to implement the state constraints, you need to have this penalty function, which is of a secant form. So again, both these error control and this penalty function is of trigonometric form. Then what you need to do is you need to update your optimization problem, and wherever you had the control U, it now becomes U trig, which is your new mapped control. Then you need to determine the new control laws. You need to update your Hamiltonian and append or augment it with these new errors or the penalty functions. And then you have to find out the new control law based on the new Hamiltonian and the new control. When your control is of a bang-bang or singular form, you get two options, which are shown here. And then if you are trying to solve for a problem where there are constraints on controls and controls appear in a nonlinear form, based on the order of nonlinearity of the control, you might get, say, p+1 solutions for a pth order control. So one solution corresponds to the minimum value of the control, one solution corresponds to the maximum value, and then there are in between controls. Now, since there are more than one options, you need to use Pontryagin's minimum principle to find out the best control option at each point whenever you calculate or make the calculations. Then in the fifth step, you need to calculate the dynamics for the co-states, and these are the new dynamics. As you know, the co-states impact the controls and the control impacts the states, and that's why we need to do this step. And then in the last step, you need to solve for a 2-point boundary value problem, and the stress is on the word 2, and you don't need to solve for multi-point boundary value problem. So there is a huge advantage of using this methodology. So first, talking about the very first class of problems where the controls appear in a linear form in the system of equations. These problems are popularly known as bang-bang and singular control problems. So here the control appears, or the control constraint appears in this form, and then you can write the Hamiltonian in this special format where there is a switching function, and traditionally you will get this set of solutions like I discussed before. The problem with the bang-bang controls is that the control stays either at a minimum value or a maximum value, and when the control switches from a minimum to a maximum, there is a very sharp jump. But now we are trying to solve optimal control problems, which involves dynamics of states and co-states, and all of these are continuous in nature. So when you have these sharp jumps, then it leads to numerical issues. So you don't need these sharp jumps. You need a smooth version of this structure. Second problem arises with these singular controls where there are just too many options or too many controls, and you need to evaluate a singular control law. So when you follow the traditional approach, you need to use something called the generalized Legendre-Klebsch condition, also known as Kelly's condition. In this, what you do is you take the time derivatives, odd and even time derivatives of the control law until the control appears explicitly in the even time derivatives. So you need to keep taking those derivatives, and you don't know how many times you have to take those derivatives. So this process is overall very complicated. Instead, what you can do is you can just resort to this new method, the UTM, and then you can map the control from U to U trig and make sure it stays between a minimum and a maximum. Place implicit bounds on this control. You need to introduce a small amount of error. As I said, you need some smoothing in the control structure. So this epsilon, or the error parameter, brings that smoothness factor, and this control term, the error control, also takes this smoothing into account. So overall, this epsilon cos trig function, this implements the smoothing structure. So based on this new Lagrangian, you need to modify your Hamiltonian, and then you obtain this new control law where again you have these two options, and you can see it depends on the switching function as well as this error parameter, and then you are able to obtain a smooth structure. Also, when you solve these singular control problems, when you have a small amount of error, you are not solving for the exact singular control problem, but you are solving for a near singular control problem. And for this near singular control problem, you will always have a unique solution. So that way you are able to avoid this non-uniqueness issue. So that is one way of getting around these. And we know that we are introducing a small amount of error in both of these types of problems, but then these are good enough to get a sense of the solution as well as for conceptual study. So how this smoothing works is you start with a big value of epsilon or the error parameter, and you make it smaller with the numerical continuation technique, and when the error parameter is small enough, you will all get a very close bang-bang type of structure starting from a very smooth structure. So that is how it works. Now, in order to showcase the utility of the UTM for these kind of problems, I chose to use a famous benchmark example called the Goddard rocket problem, where the objective is to maximize the altitude of a rocket which has a certain amount of fuel, and these are the equations of motion for that rocket, and there are certain constants involved, and then these are the boundary values for that problem. All we need to do is to introduce a small amount of error involving an error parameter and an error control, and then we change the control which is thrust to this form, which makes sure that it stays between 0 and T max. So that way we get two control options, and we use Pontryagin's minimum principle to find out the best control at each instance. And then I solve this problem using the unified trigonometrization method as well as GPOPs too. So when I solve this problem using a one-phase approach, which means I solve the entire problem in one go and not break it into three phases, which is a bang, singular, and bang. So then when I solve it using one phase, you can see there are slight errors at the entry and the exit of the singular control. So what that means is, when we are using direct methods, since they are not using the first order necessary conditions of optimality, they are at times not able to guess good control law, especially for the singular part of the problem, and there are a lot of jitters, especially at the singular zone. So instead, when you are using GPOPs 2, you have to break this problem into three phases, which is a bang, singular, and bang, and you have to enforce the conditions. While solving the singular part, you still have to resort to optimal control theory. So that means even while using direct methods, you have to still use some knowledge about indirect methods or optimal control theory in order to solve the singular part. So that shows that the problem formulation part is still very difficult. But when you use unified trigonometrization method, you actually only solve it as a one-phase problem and as a two-point boundary value problem, and in between part is automatically implemented based on trigonometric functions. The results are in excellent agreement with each other, especially for the three-phase version of the pseudospectral method-based solver. Now moving on to the second class of problems where there are constraints on the controls and the controls appear in a continuous version, or they are in a nonlinear form. So for these problems, again, the constraints are upon the control, but then using the traditional approach, what you need to do is you need to augment the Hamiltonian with these constraint conditions, and you have these extra multipliers. That makes the problem formulation and solution process more complicated, and you have to solve for a multi-point boundary value problem. So instead, what you can do is you can again map the control from U to U trick and make it implicitly bounded. And then you get here, in this case, you get three solutions. You again use Pontryagin's minimum principle to see if it's a minimum or a maximum or in between. And then you just solve for a two-point boundary value problem. So it becomes so much simpler. In order to showcase the utility of the UTM for this particular class of problems, I chose an interesting example, which is a Mars planar arrow capture problem, where the objective is to minimize the time of flight for the arrow capture of an entry vehicle. These are the dynamics involved, and I know that this problem is only for demonstration purposes, so that's why the objective is to minimize time of flight, but there could be more realistic objectives such as minimizing the heat load on the entry vehicle. There are certain other expressions involved in the equations of motion. The thing to note is that control appears in a quadratic form in the equations of motion. And then these are the constants involved in the problem, and these are the boundary values for this particular problem. All you need to do is you need to change the control to a trigonometric form, and then you obtain these three different control options. You need Pontryagin's minimum principle to find out the best control option at each instance. The first option corresponds to the minimum value for the angle of attack. The last option corresponds to the maximum value of angle of attack, and there is an in-between solution which actually maps to the optimal control law for an unconstrained problem. So there is a relationship between that as well. So this gives us a great insight about the problem structure, and which is why the indirect methods are very attractive. Then when I solve this problem using the UTM as well as the pseudospectral method-based solver GPOPs 2, the results match. They are in excellent agreement, and there is the constraint upon the control which is active for certain amount of time, which you can see in this picture. Now moving on to the third and the last class of problems, which are the most complicated version, where there are constraints upon the states. In these kind of problems, the constraints are of this form, and like I said before, You need to again augment the Hamiltonian with these extra conditions, and along with this modified Hamiltonian we need to have the continuity of the states, the continuity of the co-states at the exit, the jumps in the co-states. There are so many other things involved, the tangency conditions. So this is very complicated, much more complicated than any of the previous classes I talked about, and still you have to solve a multi-point boundary value problem involving so many points and so many arcs. Instead, what you can do is just modify the path cost of the problem, and you need to augment a penalty function which makes sure that whenever the constraint is violated, then this thing becomes infinity. This term starts approaching infinity. So that's the idea behind using these penalty functions. Now with this modified path cost, you change the Hamiltonian and you get a new Hamiltonian, and then you modify the dynamics of the co-states, and that impacts the control, and that controls, or the new controls, impact the states. So then you solve for a very simple 2-point boundary value problem. And how you solve this is that you start with a large value for this weighting parameter epsilon here, and at first you might be violating the constraints upon these states, but then the solution reveals itself as soon as you decrease the value of the epsilon, and eventually you get what you want. Now how this secant penalty function operates is that whenever the value of s approaches s min, or a minimum value, or s max, or a maximum value, then the argument here becomes plus or minus pi by 2, or secant of plus or minus pi by 2 is actually 1 by 0, which is infinity. Remember that our objective is to minimize the Hamiltonian, or minimize the cost functional, and when this particular term starts becoming infinity, it is going against our objective of minimizing the Hamiltonian. So that's how this is like of a conflicting nature. We need to minimize something, but then that minimization is actually becoming a maximization, or infinity. So therefore the bounds are emplaced upon the state constraints. So constraint violation is avoided in that way. In order to showcase the utility of the UTM for this particular set of problems, I chose an example problem from the thesis of one of my colleagues who have been doing a very good work. The problem here is to maximize the terminal energy of an hypersonic vehicle entering into the Earth's atmosphere, and there is a heat rate constraint as well as an angle of attack control constraint upon this problem. So this is a great example to show that if there is a state constraint as well as a control constraint, how the unified trigonometrization method can simultaneously solve for both of them. So here is the objective functional, and then there are these dynamics for this problem, and there are these expressions which are used in these equations of motion. Again, the control appears in a quadratic form. These are the boundary values upon the problem. All we need to do is to append this penalty function, which is of a secant form, and there is this weighting parameter, and then there is a constraint upon the control as well. So then we modify the Hamiltonian and we get a new Hamiltonian based on this penalty function, and you get a new control law because there is a constraint upon the control as well. So you get something like 3 control options in this case, and again you use Pontryagin's minimum principle to find out the best control option. The co-state dynamics are modified and you get a new dynamics for the co-states as well. And I have shown these new co-state dynamics, and the changes to them are shown in green. You see these are very minimal changes, and one thing I can assure you is that I did not do any of these equations I have not typed by hand. All these are using automated techniques employing symbolic toolboxes. So these are recent advancements made in the indirect methods, which have made them very much more attractive than before. So you don't need to fear of these equations, but you need to know that there are these equations involved, and that's why you get very high resolution results. Now when I solve the problem using the unified trigonometrization method and GPOPS2, the results match, the constraint is never violated, and it's active for a certain amount of time. One other thing to note is that in literature many times these error parameters are mentioned just as numbers, but actually they do have units, and when you are doing something called unit scaling, these will come into picture. So always we should mention them along with their units. Also, one thing to note is that if we start with a large value of epsilon and march towards a smaller value, beyond certain small value, you don't really need to make it even more smaller because there is not much improvement in the result. So you can leave it to 10 to the power minus 3 in this case. Those results are again in excellent agreement with GPOPS2. And if you solve it using a traditional approach, you have to actually solve for a 5-point boundary value problem involving 4 arcs, and you can see the control constraint is active as well as the state constraint is active. So this is a great example of showing how both these constraints can be simultaneously solved by the UTM. The stress is again on the word simultaneous. So in the end, I would like to summarize the presentation. I introduced a method called the unified trigonometrization method, which can simultaneously solve for any number of control and state constraints. And all of these are done through trigonometric functions, and that's why the name is unified trigonometrization method. Now we can solve 3 different classes of problems. One which have bang bang and singular controls, where we introduce small amounts of error of trigonometric form. Then there are problems involving constraints on controls, and controls appear in a nonlinear form. Again, we change the control to a trigonometric form. Very easily we can solve those problems. And the third class of problems is where the constraints are upon the states, and we introduce these penalty functions which are of secant form, again a trigonometric form of imposing constraints. And then if you see, there are just very minimal changes to the original problem, so that makes it very attractive, this UTM technique. And then you can solve various classes of problems. I have showcased some very simple examples to demonstrate the utility of the UTM. And then the results obtained by this new method matches with those obtained using a pseudo-spectral method-based solver called GPOPS2. Future work regarding this study involves applying this UTM framework to other domains as well, and not just atmospheric flight mechanics. And we have been looking into chemical engineering problems, medical science problem involving tumor treatment using chemotherapy, and renewable energy and whatnot. And then also, we like I mentioned before, I'm not claiming that I can solve all types of optimal control problems involving different types of constraints. So we have to still look to extend this framework to those other sets of problems involving other kinds of constraints. There are problems called minimax and maximin. So those can benefit using this method. So thank you so much for your time and for listening to this presentation.